Okay, let's get started with our lab. We have charging, discharging RC circuit this week, and we're going to measure the time constant. So an RC circuit just has a resistor and a capacitor in series with each other. And our power supply. So this is for charging. RC circuits, R for the resistor, C for the capacitor. So it has a resistor and a capacitor. And we'll do an RL circuit later on. We'll do a inductor. L stands for inductor. Inductor resistor circuit. It has a time constant also. We'll measure the time constant of that circuit later on in the quarter. So this is for charging, right? We close the switch. Here, if we have a switch here, we close the switch and we charge the capacitor. And then we could take a charged capacitor and hook it up to a resistor, close the switch, and it will discharge through the that resistor, and the charge will drain out. So where do the equations come from that govern this behavior? Well, we do a simple loop rule. We go around the loop and we add up the voltage rises and drops, and when we get back to the same point in the loop, we say all the rises and drops have to add to zero, because electric potentials are kind of like elevations. When you're going on a hiking trail, you go up a hill, you go down a hill, up a hill, down a hill. If you end up back where you started, you have to be at the same elevation again, right? You can't be at a different height, a different elevation. It's the same with electric potential. So we can go through this circuit and add up all the potential rises and drops, and we get zero when we add them all up. So this is the circuit diagram that we just looked at, right? We've got a capacitor and a resistor in series, and we've got a special switch here. This is called a double throw switch, because you can hook it to one position or another position. So when it's thrown to position A, we're in a charging capacitor mode, right? We've got a battery hooked up to our RC circuit, or resistor capacitor circuit. And when we throw it to B, we just have a wire connecting them, and so the capacitor can discharge in that state. So here's the equation for the discharging circuit. Q over C, that's the voltage on the capacitor, and IR is the voltage across the resistor. So this equation 1 gives us the loop equation, the sum of all the rises and drops in the circuit, and it has to equal 0. Well, we know that I is the change in current with respect to time, di dt. So if we put that in there, this becomes a differential equation, and we can solve for Q. So when you do the math and solve the differential equation, you get the charge on the capacitor as a function of time is this equation 2 here. It's an exponential. E to the minus t over RC is what it turns out to be. So what that tells us is, let's think about what happens to the charge on this capacitor when t goes to 0 and when t goes to infinity. I like to think about those endpoints. So this is a discharging capacitor. So what is the charge on the capacitor at t equals 0? At t equals 0, the capacitor has to be at maximum charge, right? Full charge. So Q naught. If we plug that into our equation, does it work? Yes, e to the 0 is 1, so q at t equals 0 is q naught. And what happens when t goes to infinity? We hook this capacitor and resistor up. What happens as t goes to infinity? The charge has to drain all the way to 0. And when you put t equals infinity in there, you get e to the 1 over 1. We get 1 over e to the infinity power, or 0, right? The charge goes to 0 as t goes to infinity. So it all makes sense mathematically. I just want you to think about it a little bit. That way you know you have the right equation for charging or discharging. Make sure you have the right equation because they do opposite things, right? One starts at 0 and goes to Q max, and one starts at Q max and goes to 0. Make sure you have the right equation. Okay, so there's our charge as a function of time. And this is what it looks like. Charge as a function of time. Or it's hard to measure charge, right? Charge is a really hard thing to measure. But it's easy to measure potential difference. We can hook up a DMM. In lab, we would use an oscilloscope to do this. Now we're going to use a digital multimeter. But we'd hook it up, and you can measure the voltage across the capacitor. And we know Q equals CV, so they're proportional. We can measure the voltage, and it's proportional to the charge. It's good enough for us. So we can use equation 3 just the same way we would use equation 1 for charge. Now, what ends up happening here is, let's say you and I both made an RC circuit, and we want to compare them. I say, well, how long does yours take to charge up to maximum charge? You would say it takes an infinite amount of time. And I would say, hey, mine also takes an infinite amount of time, right? Technically, that's true. We know that there's diminishing returns after a while, and for all intent purposes, it's maxed out at some time before we get to infinity. But as far as the math is concerned, it takes an infinite amount of time. So we can't really compare our circuits that way, right? So maybe we could say, well, how long does yours take to get to half of its maximum charge? That would be useful, right? That would tell us the rate, which one of our circuits is charging or discharging at a faster rate. But if you look at the equation, I mean, we could do it, right? We could figure out when does V equal half of its maximum. It's not that hard to do, but it doesn't naturally fall out of the equation. But what does naturally fall out of the equation is when does the voltage equal 1 over E times the maximum voltage, right? Because when T is equal to RC, we get the voltage on the capacitor is 1 over E times the maximum voltage. Or the charge on the capacitor is 1 over E times the maximum charge. That kind of falls out really nicely, right? It's right there in the math. We don't have to do any math in our head. It just falls out really nicely and easily. So that's what we use. When we want to compare charging rates and discharging rates of RC circuits, we have something called the time constant, and that's tau. And when T is equal to tau, the time constant for the circuit, it's equal to RC. The time that it takes our capacitor to discharge to 1 over E of its maximum value is the time constant of the circuit. And like I said, we could have said half of its maximum value, but then we'd have to do some math every time to figure it out. This way we can look at the equation and see T has to equal RC to get to 1 over E of its maximum value. And that's shown in the graph here. If you know what the maximum value is, 1 over E of that, right, 37%, and then you find where the time is, what time interval elapsed for it to go to 1 over E of its maximum value, and that's the time constant of the circuit. You could also do the same thing for a charging capacitor. You would get a different equation for charging. Instead of just E to the minus T over RC, you get 1 minus E to the minus T over RC. You get a slightly different circuit there, right? And so for that one, if you started at 0, you would go to 1 minus 1 over E, which is 0.63 times the maximum. and that would be your time constant. So what are we going to do today? We're going to measure the time constant of a circuit, and we're going to do it 3 different methods. Method 1, you're just going to multiply R times C, right? The time constant is R times C. So you're going to measure R. Well, you're going to watch a video of somebody measuring R. You're going to watch a video of somebody measuring C. You're going to multiply them together. And that is your first time constant measurement, tau 1. Then you're going to do what I call the single point method. You're going to just do the calculation here. Where's my graph? You know what voltage you're starting with, your starting voltage, the maximum voltage on your capacitor when it discharges. And so you're going to multiply that by 1 over E and just advance the video until you get to the time when the voltmeter reads that new voltage, that new calculated voltage, 1 over E times the maximum, and record that time. That's tau. All you're doing is looking at one data point, the time when the voltage is 1 over E of the times the maximum. Okay, so that's method 2. You're going to use this this relationship and just get the data right off of the video you're watching. Method 3 we call the multiple point method, because you're going to do about 40 data points. Where is it? Method 3. You'll take about 30 to 40 data points off the video as you're watching this thing charge or discharge over time, right? You're going to take data points over time, and you'll plot them and try to get tau from that. But the easiest way to do that is to turn it into a linear plot. So here's some information on that. This is how you would do it for a charging capacitor, but you can do the same thing for discharging. So here's the equation for a charging capacitor. The voltage across the capacitor is the maximum voltage times 1 minus e to the minus t over RC. So the first thing you do is you start rearranging things. You want time all by itself, all the terms with time on one side of the equation and everything else on the other side of the equation. That's the second line here. Then you take the natural log of both sides. And when you take the natural log of e to the minus t over RC, you get minus t over RC, right? You might have to review your log properties. And then you see that this kind of looks like, where is it? This kind of looks like an equation y equals mx plus b. What's y? What goes on the y-axis? The natural log of 1 minus the voltage on the capacitor divided by the maximum voltage. If I plot that as one item in a spreadsheet program, and on the other column I have time, and I plot them against each other, I should get a straight line. And what should the slope be? Minus 1 over the time constant of my circuit, minus 1 over RC. So I can plot that and get the slope, and then figure out what my time constant is. It's negative 1 over the slope. What you're going to do, you'll actually end up with five measurements, because you'll do, where is it here? There are 4 equations in this document. There's charge on the capacitor as a function of time. We just talked about that, right? And that's we can look at that while it's charging, and we can look at that while it's discharging. And then there's current in the circuit as a function of time. And we can look at that while it's charging and while it's discharging. I don't think it's necessary for us to do both current and charge. We'll pick charge. All we're going to look at is charge. But we are going to look at it for charging and discharging. So we're going to do what I call here A and B. We're going to do A and B. If you really want to do C and D, you can convince yourself that the current does obey these same equations also. But I think once you've done one of these, once you've done charge, I think you can take a leap of faith and know that the current will also obey those same equations. So we've got method 1 here. You only have to do that one time because R and C stay the same for charging, discharging. So you do method 1 one time. Method 2, the single point measurement. You're going to do that once for the charging circuit and another time for the discharging circuit. So you're going to have 2 taus there, one charging, one discharging. And then method 3, the multi-point measurement where you linearize it and get the slope is 1 over their time constant. You're going to do that for 2 methods. So you're going to have you're going to have the 2 graphs for that. So that's for charging and for discharging. So in the end, you'll have 5 time constants, okay? And you'll make a little table and compare them. And it would be nice if you had uncertainties on each one, okay? So see if you can figure that out. Method 3, where are you going to get the uncertainty? You're using a slope in a line in a spreadsheet program. You're going to get the uncertainty from linist, okay? So think about that a little bit. Method 2, you're just getting the uncertainty from the meter, right? From you're looking at a meter and getting a voltage at a certain time. So think about how you would get the uncertainty from an instrument like a ruler when you just took one reading. It's going to be some percentage of the smallest increment on that measuring device, right? Same with method 1. You're going to get the uncertainties in R and C and see how they, from the measuring device, some fraction of the smallest increment on the measuring device. Just a quick refresher on uncertainties and error propagation. When you're multiplying 2 things, what are you going to be multiplying? R and C, right? When you multiply these 2 things. So tau 1 is just R times C. And how are you going to get the uncertainty in that? The uncertainty in tau 1, you're multiplying. So when you multiply things, they could have different units. In this case, they have different units, right? Resistance and capacitance, different units. You can't just add up or numbers that have different units, right? So we convert them into percentage errors. We take the error in R divided by R, and that has now changed it into a percentage error, right? Unitless quantity. And we do the same thing with the capacitance, the error in the capacitance over the capacitance. So that's a percentage error. And what do? We square them, we add them, and we take the square root. We square them, we add them, and we take the square root. And now we have the percentage error in our time constant. But we don't want percentage error. We want just error with units of seconds, like our time is. So we multiply that by tau 1. And that gives us our uncertainty in tau 1. And then how do we report that value? Tau 1 plus or minus sigma 1, right? Units of seconds for both of those. It might surprise you that resistance, units of ohms, and capacitance, units of farads, multiplied together gives you seconds. But it does. So you can check that if you're curious, but you can take my word for it. Okay, so error propagation, that's one thing we're going to do. And then the other thing is for linist, right? So what does linist tell us? The error in the slope. So we have a value here for the slope, m, and we have the error in the slope, right? We have m plus or minus some error, right? This is our slope. But we don't want our slope. We want the reciprocal. We want 1 over our slope. Tau is equal to 1 over the slope, right? This is for tau 3, I guess we could call it, right? So our tau 3 is going to equal 1 over the slope. And the question is, what is the error in that measurement? So what we have to do is turn the error into a percentage error. Because the error in the slope, if we turn it into a percentage error, the error in the slope is the same as the error in 1 over the slope, right? The error in x as a percentage is the same as the error in 1 over x as a percentage. It's not the same if it's not a percentage, right? Because we're changing the value quite a bit. So what the percentage error, so let's write this. Okay, the percentage error in x is the same as the percentage error in 1 over x. Let's move, oops. So that means that we want to figure out the error in tau, right? We know the error in the slope, and we're taking 1 over. So we say sigma m, the error in the slope, divided by m, is the percentage error, right? This is percent error. So that's going to be the same as the percentage error in 1 over the slope. So we can multiply that by 1 over the slope, and that will give us the error in 1 over the slope. And what is that? That is sigma 3, right? The error in tau using method 3. We've got a tau 1, method 1, right? We've got a tau 2 for charging, and we have a tau 2 for discharging. And then with method 3, you've got a tau 3 for charging and a sigma 3 charging, and a tau 3 discharging, sigma 3 discharging. Okay, so those are the 5 things. And you'll have 4 graphs. Okay, 4 graphs. One graph is here, and one graph is here. Those are the 2 that you're getting the slope from. But I also want you to do the 2 graphs before we linearize them so that you see that exponential, the discharging and charging exponentials. I want you to see that you get what those same pictures that we showed you in the lab write-up earlier, you're going to get those from the data. So you're going to have 4 graphs. So you're going to get a charging and a discharging, the exponentials, right? And then the charging and the discharging, the linear plots used to get tau. This is for method 3. The graphs are for method 3. Method 2 is just a single point measurement. You're looking at a video, you just record the time from that. No graph for method 2. Method 3, the graphs are all for method 3. Okay, so what I want to do is show you that video real quick so you know what to expect. So here's the video you're going to watch, and it shows you the circuit. This is the charging circuit, and here's what the circuit looks like. There's a little 9-volt battery hooked up there. That's our power supply. And the discharging circuit is the same capacitor and the same resistors. For some reason, they used 2 resistors. I guess they didn't have one that was big enough, so they put 2 in series. Here's the voltage on our battery, right? So you have to be careful. Whoa, whoa, whoa. Okay, so when you see an image like this, you have to be careful, look carefully how it's set. This is set to 20 volts DC, and it's reading 8.33. So that's volts right there. That's 8.33 volts. All right. Now if we look at our next one, we're measuring the capacitance. And so this is 1.18 millifarads. Millifarads. The lowercase m is milli, 10 to the minus 3. Okay, so that's a pretty big capacitor. I think we've talked about the fact that capacitance is usually like picofarads or nanofarads. This is only 10 to the minus 3. So this is a pretty large capacitance, and those resistors are pretty large. It's 40,000 ohms, I think, is the resistance. Okay, so now if we jump ahead a little bit, here's their total resistance. So if I stop this here, total resistance, it's reading 43.7. But 43.7 what? Well, look at the dial is set to, what's it set to? 200 kiloohms maximum. So this is reading in kiloohms, 43.7 kiloohms, right? Times 10 to the third ohms. So be careful when you're taking your measurements. Now let's jump ahead. We've got a circuit here, and this is the charging circuit, right? So it says that right on the bottom. And she started the timer at the same instant she closed the switch. And so you can see here the voltage on the battery is, on the capacitor, that's the one we care about. We don't care about the voltage across the resistor because that's how we get the current in the circuit. And I said we don't have to do the current unless you want to. So the voltage across the capacitor, that's the one we care about, and the time. And you're just gonna hit play, let it go for about 6 or 7 seconds, and pause, and then write down the reading. So 0.9 volts and 7.32 seconds. And then you're going to go for about another 7 seconds or so, and hit pause, and record 1.61, 13.01 seconds, right? And then you're going to go for another 7 seconds or 8 seconds, and do the same thing, right? And so 2.37 at exactly 20 seconds, right? So you're just going to keep doing that until you have, 35, 40 data points, something like that. And that'll be where you get your data for method 3. Okay? This is charging. So charging goes all the way out to about 8 minutes or so, I think. Let's see, where does she? 5 minutes. She goes out 5 minutes and then stops. And then she switches over to the discharging circuit. And so now for discharging, you can see it starts out at its maximum value, 8.07 volts at time 0. And then when everything starts, there are 8.06 volts. And you can see the voltage starts to come down right away as the time goes up. And you're going to do the same thing. You're going to stop, record a data point, go 7 seconds, 8 seconds, stop, record a data point, and just keep going like that until you have 30 or 40 data points. Sometimes out at the end, near when the voltage is hardly changing, out at the end of the time, the data doesn't work out as nicely. So it's better to keep it into, I know this goes out 5 minutes, I would say don't go more than 4 minutes on your data collection. Stop when you get to 4 minutes. Don't go more than that. And when you plot it, if you have some points at the end of your plot that don't look right, that don't look like they're following, the first 30 points might be a nice straight line, the last 10 might deviate a little bit from that, then justify not using those points because things aren't changing very much there and you can get a lot of noise in the data. Okay, so this is how you're going to get your data. You're going to watch this video. There's a link to it in the handout. We've gone over some of the other things, the how this all comes to be, right? We're trying to come up with a way we can compare circuits. How quickly is mine charged compared to yours, or discharged compared to yours? And so it's this time constant involved. And we've talked about different ways to measure them. We're going to use 3 different techniques to measure them. We're going to measure both charging and discharging, so that means 5 time constants. And 2 of them involve graphing, and you're going to first do the graphs that just show that they follow exponential curves. And so that's just kind of a visual, but you're going to turn those in. And then you're going to do some math in Excel to convert those into linear things. So you're going to take natural log of one column, and then you're going to plot that against time. So you're going to have to manipulate the data a little bit in Excel. So make sure you're not doing log base 10. You know, with formulas in Excel or some spreadsheets can be tricky. Make sure it's not log base 10. Make sure it's a natural log when you select the function in your spreadsheet program. For the video, I would watch no more than 4 minutes of the 5. So I think they're each 5 minutes, maybe one's longer. I wouldn't go more than 4. And so 40 data points, what was it, 30 or 40 data points at 4 minutes, I think it comes out to a data point about every 8 seconds. So, you know, somewhere in that 7-8 seconds, your stop. It doesn't have to be equal time. Don't try to get it just right and back up and forward to try to get it exactly 7 seconds apart or 8 seconds apart. It doesn't matter, right? You're just plotting a bunch of points. If some of them are 7.3 seconds apart and some are 7.9 and some are 8.2, it doesn't matter. In the end, you're just putting a best fit line through them. So just stop the video, take a data point, right? Voltage and time, hit play, watch when it goes about 7 seconds or so, hit pause, take another data point, and do that until you've gone out about 4 minutes, and then stop, and you should be good. Okay, if you want to stick around for Excel, we'll talk a little bit about Excel. I'll continue the recording. If you know about it, how to use spreadsheets and take the natural log of one column and plot that against time, then there's no reason for you to stick around. So everything should be posted and ready for you to do the lab. Spreadsheets, what are they good for? Repetitive calculations. That's the one thing they are just a dream at. If you're doing the same calculation over and over again, spreadsheets make that very easy. And so what would we be doing over and over again here? We would be taking the natural log of each of our 40 data points, let's say. If I have, let's call this the voltage, V sub C, voltage across my capacitor, and this would be time. And then I just have some values. What is it? Starts at 8 at time 0, right? And then it goes to something else, whatever, 7.5, 7.1, 6.6, 6.2, 5 point something, 9.2. Okay, you get the idea. And then the times are going up maybe every 5 seconds or so. I got 5, 10, 15, 20 seconds, 25 seconds, 30 seconds, something like that. Okay. So I've got some data here. I'm just making it up. And what I want to do, I want to create a column called natural log of V. And so you start out with an equal sign. That tells Excel you're inserting a formula there. And then, let's see, I've got ln. Oh, look at that. So look, these are all, I just start typing in what I think the formula is going to be. I just typed an L there. And I look, and all these functions come up that start with L. Linus is one that we're going to use later, but not right now. There's natural log. There's log base 10. There's this log. I don't know what that is. So I'm going to click natural log. It says returns the natural log of a number. Okay, that's what I want. So I'll click on that. And then it says what number. So I will click on my cell that I want it to look at, and I'll close the parentheses and hit enter. Now I can grab that cell and drag it down. And when I drag it down, it should change. So this cell is looking to the left at A2. The one below it should look to A3. Excel anticipates what you're trying to do, and so it figures out that you're doing that. Sometimes you don't want to do that. Sometimes you always want it to reference the same cell. And if you want it to always reference the same cell, you put a $ in front of these. So if I always wanted it to be in column A, I could put a $ in front of the A. If I always wanted it to be in column 2, I could put a $ in front of the 2. So now 2 is frozen. So if I drag this down, I should get the exact same value because every one of these is looking at A2, A2, A2. They're all looking at 2 because I froze A2. It won't move, increment it with the row as I drag it down. So we'll go back, but if I drag it to the right, it will change the A to a B. So this is going to give me an error because it's trying to take the natural log of 0. This should give me a nice number. What's it doing? B2. B2 is 0. Yeah, so all of these are giving me B2, right? So when I drag them over, it moved, all the A's became B's because I don't have a $ in front of my B, in front of my A. But the 2 is frozen. It has a $ there. It's locked in. If I dragged it over again, I'd get C now, right? We good with that? Okay, so let me take away that $. The $sign is really nice if you want to change something later. So let's say you have a whole equation that's based on the temperature being a certain value, right? So if the temperature is a certain value, your whole equation becomes one thing. But if the temperature changes, then it changes stuff in the equation, right? So you can do you can have a cell up here and call it temperature and put some value in here. And then you can, in your equations, you can lock this cell. So as you move everything through your equations down, that's locked. And then you can say, okay, I've seen all the calculations for 100 degrees. Now I'm just going to go to this one cell and change it to 90 degrees and then see what happens to everything else in my spreadsheet. So that's kind of nice for that. Okay, so here's our natural log. And then you want to plot time on the horizontal axis, right? And the natural log of your voltage on the vertical axis. And so I can never remember in Excel which way it goes. I think the x-axis is first. So I'll move, delete. Okay, so I've got 2 right next to each other. I believe the one on the left shows up on the horizontal axis, but always check. So we will do a insert, a scatter graph, always a scatter graph. I'm still getting graphs with lines connecting the points. Scatter graph, okay, there we go. No lines connecting the points. Just show me on the graph what you measured. You measured one data point for each of these values. Don't show me stuff in between, okay? Now let's make sure it graphed properly. So time goes from 0 to 30. 0 to 30. And natural log of my voltage goes from 1.6 to 2.0. 1.6. So it looks like it graphed the way I wanted it to. So always check. Make sure what you think is on the x-axis is actually on the x-axis. And what you think is on the y-axis is plotted that way. So there's my plot, and then you do your linear fit, right? You click on this and insert a you click insert trend line, and when you insert the trend line, always click more options, and then display the equation and the r squared value. Okay, you always want that equation, right? Well, I don't know why you would insert a trend line if you didn't want the equation of the line, but you have to do that. If you're using Google Sheets, it's kind of hidden in there. It's in the title, or the label, I think they call it, for the line. You have to go to where it says label or title and change it to a display equation, or use equation, I think it says. So make sure you see the equation. Okay, we done with this? Go away. There we go. So there's our equation. And that's the slope of the line. Okay. And then there's an Excel and Google Sheets video on how to do Linist from week 1, I think, right? So go check that if you forgot how to do Linist. But Linist gives you the error in the slope. All right. Any questions? And you can always add and subtract too. So this is for discharging, right? It was more straightforward. But for charging, it's 1 minus e to some power. So you just create a cell here and add 1 to everything, right? Or subtract 1 from everything. So it's very easy to do that. You record the voltage. You can divide by a constant, right? So I can have my data here, and then I can have a column that says VC divided by E max, and so this is going to be equals the value divided by 8, right? The maximum in my case is 8. And then you drag down, and you can see that this is also going to be this value, 7.5 divided by 8, 6.6 divided by 8, right? 5.2 divided by 8. And actually, I don't even have to do 2 steps. I could do it all in 1 step. I could say this is going to be 1 minus that. And then I can come here and say this is equal to 1 minus A23 divided by 8. And then I can drag this down. And so this should be 1 minus 7.5 divided by 8. 1 minus 6.6 divided by 8, right? Now I can take the natural log of that. I could do another column here, taking the natural log, or I could do it right here, right? Oops. ln of all of this, right? I could do that. And this is going to be equal to natural log. It's not going to like this one. It doesn't want to take natural log of 0. But that's okay. Okay. And so there are my values. The natural log of 1 minus V capacitor over V maximum, right? So you'd use that for the other situation where you have a charging capacitor. So you would never get to V maximum. So you're not going to have a 0. You're not going to have an undefined point. You start at V equals 0, and you keep going until for about 5 minutes or so, 4 minutes, until you're up at a higher voltage, but not all the way to V maximum.